Okay, so let's look at actually a specific forcing function. So we're going to force it by, let's see, I've been using red for forcing. So we're going to force it by something that looks a whole lot like the actual solution. We're going to, at time 0, we're going to turn on the forcing, and we're going to push it at its natural frequency. And we should know, hopefully you've seen in a differential equations kind of class, that that's going to make this thing resonate. Well, this is also something that you do all the time, anytime you're like pumping a playground swing or something, um, that if you push something with exactly its natural frequency, you're going to add energy to it continually. Okay, so remember, we're going to use U is 1 over m omega times exactly this function. And we discovered last time that that is the right kind of thing to get the causality right, and in particular to guarantee that it's the solution that was not doing anything at past infinity. So we're definitely, that's a confirmation that this really is the right thing to use. And so let's just calculate it. Y was just calculating a convolution. It's just a little fun with, so y of t, just make explicit, is this of t. Oh, and what is it going to be here? It's going to be 0 up to here. The support, we know the support is going to be 0 all the way up to 0. Nothing's happening until 0, that's fine. So now for t greater than 0, what's going to happen? Just to be really clear about what the inequalities are going to be. Okay, well the 1 over m omega is going to come out. And then by definition, we do this integral from minus infinity to infinity. We know with a bunch of step functions, that's going to collapse pretty quick. This is something we talked about way at the start of convolutions, which is you often see in this initial value problem context, especially if you assume everything starts at or after 0, you see this alternate, quote, definition of convolutions where you don't even try to integrate from minus infinity to infinity. This guy is only going to start at 0, and this guy is going to turn off. If tau is bigger than t, that'll be negative, and so it goes from 0 to t. And so that's what you commonly see as an alternate definition of convolution in the initial value problem setting. And I talked a long time ago about how that's not an alternate definition. It's just a little easy theorem that if your functions have these h's in them, then it'll collapse. It's convenient because you know it's not an improper integral. No worries about supports and all that kind of stuff. Okay, and convergence. Okay, so what's that going to do? Well, we've got a product of sine functions here. And we've got this nice identity, sine A sine B. If you play with the cosine and sine sum rules, actually the cosine difference and sum rules a little bit, you can get a nice little identity. It's very, very helpful, and we're going to play with this a lot with the Fourier once we really go with cosines and sines a lot more. That's 1/2 cosine of the difference minus cosine of the sum. Got to get the signs right. Okay. And so this is going to be 1 over m omega, integral 0 to t, 1 over 2 m omega. I'm just going to take the half out. Okay, so it's going to be cosine. The difference of these guys is omega times 2 tau minus t. Okay. I'm taking, let's see, I think I'm taking this as a and this as b. It doesn't really matter because this is an even function. But I think it's going to look nicer if I take this guy as a and this guy as b. And then the cool thing is that the other guy, when I add these together, the tau's cancel. It's not an accident. That's very special to this situation. And I just get omega t. Why is that special? Might have to stare at it for a second. That's a t, not a tau. That's a constant as far as the integration is concerned. Eventually, that's going to be our variable that comes out in the final answer to get a function here. But in the integration, it's a constant. So this will come out as something that we have to integrate. Okay, and it's not hard to do. I'm going to skip a step. You can do just the FTC part. Don't want to make it too long. Okay, we get this, and it turns out that's not really the interesting part. And then minus, this guy is just a constant, integrated from 0 to t. You just get t cosine omega t. Okay, so that's what we get. And let's look at that. The main thing, it's not the details so much, but what kind of function is that? Well, this is just a sine function, not particularly weird. This, though, is a t times a cosine function. Okay, that's going to grow in amplitude as we go off to infinity, and that's the resonance. It's a good double check, though, that it should start in the right way. This is a fairly gentle forcing. It doesn't start with a shock. It doesn't even start with a force at all right at the start, so it should be quite gentle. And if you calculate the derivatives carefully, the first and second derivatives of this guy actually, oh no, let's see, I think even the first and second derivatives both vanish. And so it's actually quite a gentle start because I sort of start pushing it gently, but then I'm always pushing it in that same, with the same frequency, the resonant frequency. It looks something like this. So even with a gentle start, it gets unboundedly large as t goes to infinity. So that's a nice illustration. There's lots of ways to derive that resonance, but some of them involve a certain amount of guessing, and this is just, you have to do a little bit of trig identity, but the formula is right there. You just convolve. And it turns out when you convolve sine waves of same frequency with each other, you get a little bit of an unexpected thing. You get it multiplied by a t. It's one of the more mysterious things about differential equations is you get all these sort of t's, kind of, they tell you, oh, just try this. Trust me, it'll fudge, it'll come in here. Those almost always can be interpreted as a special thing that happens when you convolve two things that are more similar to each other than they ought to be. So, in fact, maybe I should have put even more examples in. Maybe I'll do that in a supplement. Okay, so now let's go to 13. This isn't too long yet. Okay, just to get away for a little bit from being so focused on second order equations, it's just kind of cute to do this for first order equations. So we're going to look at, I'm not going to put a coefficient in front of the d, and I'm going to say minus k because it's going to match up better with stuff. So d minus k, with k is a constant. And we're going to look at Ly equals a forcing. Okay, or in other words, it's just y prime minus ky is some given function. It's the standard inhomogeneous first order linear constant coefficient differential equation. Pretty close to the simplest and most important differential equation ever. In fact, if f is 0, then it is the most important equation ever. So we would like to solve this in particular first for delta. I'd like to have Lu equals delta. Okay, and I got to make it explicit. Let's do the one that's going to give forward causality. We're going to have it do nothing at 0. Well, it should be pretty clear what's going on. Okay, nothing happens until the x equals 0. This is going to be, what's this going to be? Let's say this purple. U is going to be purple. Then I want it to jump. Okay, this is the first derivative minus a constant, but the only thing that can create a delta out of a continuous function is the derivative part. So it should have a unit jump here, and then it should be an ordinary solution to y prime minus ky equals 0, or y prime equals ky, or in other words, exponential growth. Suppose if k is positive, for example. Otherwise, it's going to be exponential decay. So it really should look like this. Okay, so there's our guess. Okay, and so the guess is that u of t is just the turn on h of t times e to the kt. Okay, so that wasn't an incredibly deductive way to do it, but it's good intuition. And let's go ahead and check it. It's a good variation on our usual technique. Let's just focus on the derivative first. Du is d of h of t e to the kt. Okay, and so the trick was, remember, let's take h of t and then multiply it by e to the kt minus 1. So we're going to turn on something that goes like this. So that's this guy, h of t times e to the kt minus 1. That is continuous. That won't have a jump. But of course, what do I have to add back in? I have to add back in the jump. Okay, so we have this nice lemma, this theorem we had, that if you have a continuous and piecewise differentiable function, then you can take the derivative in the ordinary way. And so that just says, okay, yeah, it still turns on at the origin. And that's going to be k e to the kt. Okay. And then plus the derivative of h, which is delta. Okay. And of course, that is ku plus delta. Okay, so in other words, du minus ku is delta as required. You know, a little bit of a nice practice with that kind of technique, but really it's the better way to understand it, I think, is nothing here, delta jump, and then it's satisfying the differential equation we want it to satisfy. Okay, so there's our fundamental solution, the effect of being hit with a delta and then just going your merry way, progressing as the differential equation tells you to do. Okay, so here's an example of solving a very practical equation. Let's say y of t is my money in a bank account, and I'm getting, let's see, what I call capital R, because I hate using I for interest, and I don't want to use little r. There's reasons not to do that. I want to use K. Okay. Um, oh no, R for, where that's going to be R for a rate. There we go. I don't want to use little r because that would look like an interest rate of money coming in. Oh, if you're watching this outside the United States, sorry, I'm using dollars to mean money. It's just easier than writing money. Just substitute your own currency symbol, like a euro symbol, maybe. So this is going to be, say, dollars per year, just to be definite. Okay, and then and this is going in continuously. It's just trickling in, and that's not really how money really works, but it's not a bad approximation. Suppose I get paid every day or something like that. And then this is continuously compounded. It's an interest-bearing account. Or it could be like the stock market in a very, very simplistic model where it just grows at the same rate all the time, which over the long haul is not super inaccurate. And this will be a rate of, let's say, K per year. And that K, for example, 0.05 would mean 5%. I'm not going to mess around with putting things in percents because we're doing higher math here. So 0.05 would mean 5%. Okay, so what is the differential equation there? It's just y prime. There's two reasons why your money is increasing. It is ky, that's, oh, sorry, and this is fairly important. K is going to be 1.05. Oh, no, it's 0.05. Sorry. This is an issue that comes in with trig precal. Doesn't come in here. My bad. Okay, so the rate of increase of your money is just how much money you have times the interest rate, okay, plus that constant rate of influx that you're putting in, R. Okay. But, let's say this starts, I haven't been doing it forever, then I would get infinite answers. It's the sort of causality thing again. Let's start at t equals 0, so it's actually plus RH, the unit step function. So in other words, if we put together L as d minus k, it's Ly equals a constant times h. Okay, so here's what happens if I just put a jolt of money in. Oh, let's make sure that makes sense. I have no money in my account. I jolt it, and then it grows exponentially. Oh, that's perfectly nice. And so that delta forcing is a concentrated burst of money. The analog of the impulse physically is just the total amount of money you actually put in that super short time. I forgot to say that in the PDF solutions, but that's really what's going on there. But now I'm going a little bit different. I'm saying, what if the forcing was 0, 0, 0, 0, and then I just trickle in a constant rate of money. So no, that's the rate of money. A delta rate is what you need to put in a lump sum in a short time. And a constant rate means in the very first time, in like 1 year, you haven't put that much in. And then 2 years and then 3 years, you're going to get more and more money put in. Okay, so there's definitely other ways to solve this equation, but it's a cool use of convolution. Just a good little practice. So y, as usual, is going to be u star RH. Okay, and so that the u is just a constant. R times u star h. Okay, that's r times the integral from minus infinity to t of u of tau d tau. Using the fact that starring with h is one of the most important operations ever. It's called integration from minus infinity. It's just an antiderivative operation. Okay, so let's actually put that in. That was equal to let's see, that's e to the kt, that's h of t h of tau, e to the k tau, t tau. Okay, and I think, oh yeah, and so that's going to make it equal to 0 to t e to the k tau. Okay, so now we're back to our finite integral situation, again with initial value problems, that's typical, and that's going to be r over k times e to the kt minus 1. And that's the money in your account. It's a very standard formula for annuities and things where you just you trickle money into something constantly. It starts out at 0, when t equals 0, that's going to be 0. And then it grows, and eventually the minus 1 isn't important. And it's as if you put in r over k, the rate of deposit divided by the interest rate, in as a lump sum a long time ago, and then it's been growing forever. It gets to be where it's really very similar to just plain old exponential growth. And it's just a cute example of how this works in simple cases. Okay, so we're going to go back from these kind of concrete videos. We're going to go back to the general theory, and there's some real issues about that I've been sweeping under the rug about Duhamel that come up in general. They don't come up in these examples. We've got really great answers here, but they can come up in a more general analysis, and that's going to lead us to some really cool new theory and new important theory about distributions.